All right, welcome back. Now we're starting section 2.7. Now 2.7 is a very large section which has a lot of problems in it. And these are typically word problems that deal with the concept of related rates. Now related rates are connected to that implicit differentiation that you've just finished up with, but it's dealing with word problems because of that concept of rate. Rate is usually something per time or some concept like that. And that's really the concept that we're using with this stuff. So, related rates versus implicit differentiation. Again, we have to pay close attention to notation here. In the equations with multiple variables, we were asked to find variables of a specific parts of equations with respect to specific variables that may or may not be part of the equation. Now, here comes your related rate. Maybe they may not be a part of your equation. For example, I kind of wrote this one up for you in typed up version here. Got the equation r squared equals x squared plus y squared, some equation we gave you. We would like to find dr dt, the derivative of r with respect to t. Okay? AKA, we need to take the derivative of this equation with respect to t. Take the derivative with respect to t. This is why we love that Leibniz notation. All right. So, if I have this equation, r squared, this comes from the implicit, the derivative is going to be 2r, but then you got to do time derivative of the inside, but we're taking derivative with respect to t. Now, t is not even a variable in my equation here, but every time I take a derivative of a variable, I'm going to tack on d variable dt because I'm taking derivative with respect to t here. So derivative of r squared would be 2r dr dt equals derivative of x squared, 2x, but then times derivative of the inside, dx dt. Every time you take derivative of a variable, you got to tack on d variable dt because we're taking derivative with respect to t's here. Plus derivative of y squared would be 2y times dy dt. And of course, you would like to solve, we ask you to solve dr dt, so treat this as the variable and everybody else is considered other variables or constants or whatever, and you want to solve for this guy. To solve for dr dt, I would divide by 2r and I get my equation. But in the same light, maybe we would ask you to do something else, which is, for example, we would like to find dx dt. So we got the equation 2r dr dt equals 2x dx dt plus 2y dy dt. Keep your eye on the ball. My ball is right there. I want to solve for dx dt. To solve for dx dt, I would subtract the 2y dy dt and then divide by 2x. And here comes my equation. So, subtle difference between the two. Pay attention to these two examples here. Find dv dr for the following function. Volume equals 4/3 pi r cubed. This is the formula for the volume of a sphere, something we're supposed to all have memorized. So, we want to take the derivative of volume with respect to r. But you'll notice in this example, r is my equation. So, r is the variable in my equation, so my independent variable. So this is just like the old days of taking derivatives. So if I want dv over dr, that would be, well, 4/3 pi as a constant. Leave those alone. Now, this is r cubed. Well, derivative of r cubed would be 3r squared. Now, officially, if you really wanted to see this, well, we've got to do times derivative of the inside with derivative of r, but we're taking the derivative with respect to r. So this would be like dr over dr, which ends up canceling. That's really what's going on when I take derivative of x squared and I get 2x. When I take derivative with respect to x, the dx stuff kind of goes away. So you're just taking derivative normally. So this, you can clean this guy up, of course. 3's cancel, and you end up getting your answer, 4 pi r squared. So, in other words, when I take the derivative of this guy, because I'm taking derivative of v with respect to r, and r is the variable in my equation, I'm just taking the derivative normally. So I would just, 4/3 pi is a constant, derivative of r cubed is 3r squared, and then clean it up, I get 4 pi r squared. But compare this, we're taking derivative with respect to r versus this. Now I want you to find dv dt. Take the derivative of volume with respect to time of the function volume equals 4/3 pi r cubed. Well, here we go. So I'm going to take derivative, but now derivative of v would be dv dt because we're taking derivative with respect to time equals, again, 4/3 is a constant. Constant's all over. But now what's derivative of r cubed? Well, derivative of r cubed would be 3r squared, but then times the derivative of the inside. Now, we're not taking derivative with respect to r. We're doing derivative with respect to t. So every time you take derivative with respect to t, you got to do times d variable, our variable is r, over dt. And then again, you can clean this up and you get dv over dt equals, the 3's cancel, so you get to see that 4 pi r squared, but then it's times the dr dt. So they're very similar, but when you do this times derivative with respect to time, this dv dt, every time you take derivative of a variable, you got to tack on that d variable dt, and it does come from your implicit differentiation. Now, this last one should scare you to death in terms of, I just threw a formula at you. Volume equals 4/3 pi r cubed. Now, to get into calculus, we're expecting you guys to have a bunch of formulas memorized, and I just happened to copy the one from your notes and stuff. These are the basic forms that we expect you guys to know. Now, a lot of these things, like the surface area of a box, is maybe something you don't readily know. Well, your professor usually gives you that, like surface area of a cylinder. But certain things you are expected to know, like volume of a sphere, volume of a cylinder, volume of a cone, volume of a box. Oh, sure. And even the surface area of a box. It's the area of all the surfaces. Pythagorean theorem down here, area of a triangle, 1/2 base times height, area and circumference of a circle, area of a parallelogram, area of a trapezoid, area of a rectangle, as well as the perimeter of a rectangle, and area and perimeter of squares. These things we've all had since a long time ago, 3rd grade or whatever. All right, so that being said, let's take a look at example number 1 here. I'll blow it up so you guys can see a little bit closer here, because I did type on a little small. All right. Find dv dr for the function v equals pi r squared h. Now, we're taking the derivative with respect to r, but you'll notice here r is one of my variables. But hey, we also have a different variable, h. So remember, every time you take a derivative of a variable, in this example, you're going to do d variable dr. So this is the way to do it, to kind of connect all these things together. So, what is derivative of v with respect to r? Well, that would be just dv dr equals, now I got pi r squared h. Now, pi is a constant. Let's leave that alone. Constant's held out front. What is derivative of r squared times h? Well, that is a product. Therefore, we're going to have to use the product rule. Derivative of the first times the second plus the first times derivative of the second. Well, derivative first. What's derivative of r squared? That would be 2r, but every time we take a derivative variable, we got to multiply times d, whatever the variable is, r, with respect to r, dr. Okay, yes, this is going to cancel. Plus product rule. Derivative times the second, sorry, I lost something other. Derivative of the first times the second times h, plus the first, which is r squared, times derivative of the second. What's derivative of h with respect to r? Well, derivative of h being a variable is just 1 times dh dr. When any time I take a derivative of a variable, I always have to multiply times d, whatever the variable is, dr. So notice these dr's on the bottom there. But you'll notice that dr over dr ends up canceling. So you end up getting the answer. dv over dr is equal to pi times 2rh plus r squared times dh dr. And that is my solution. Now, compare that one to the next one. What did I ask you to do? I'll leave both of these guys up here so you can see them. Find dv dt for the function v equals pi r squared h. Well, now I'm taking the derivative with respect to time, which means every time I take a derivative of a variable, I want to tack on d variable dt. So derivative of volume would be dv dt equals, pi is a constant, leave it alone. And I have, once again, r squared times h. And being r squared times h, two variables being multiplied together, I could use the product rule. Product rule, derivative of the first times the second plus the first times derivative of the second. Well, derivative of the first guy would be 2r. But every time I take a derivative variable, you got to tack on that times dr dt. Derivative of the first times the second, h, plus the first, r squared, times derivative of the second. Well, derivative of h would be 1 times dh dt. Every time you take a derivative of a variable, you take derivative of that variable times d variable dt. And now let's clean this guy up to get our solution. So dv dt would be pi times 2r dr dt plus r squared times dh dt. And there's my solution. Well, keep practicing here. Try this guy. Find dA dH for the function a equals pi r squared. All right. So to find derivative of this guy, here we go. Jump in with both feet, but remember, we're taking derivative with respect to h. H is maybe some height or something or other, but there are no h's in this equation. Don't care. Every time you take derivative of a variable, you tack on times d variable, whatever it is, over d, in this case, h. So derivative of a would be dA dh, because we're taking derivative with respect to h, is equal to, pi is a constant, leave it alone. What's derivative of r squared? Well, it is 2r, but then you got to multiply times the derivative d of the variable r over d with respect to what you're taking the derivative of, which is h. So you can clean this up. dA over dh would be 2 pi, because it looks better, r dr dh would be my solution. As compared that to, and that's a t there. What would dA dt be? Well, now we're going to take a derivative of this equation, a equals pi r squared, and we're taking derivative of every variable with respect to times. Every time I take a derivative variable, I'm going to put times d variable over dt. So, what's derivative of a? That would be dA over dt, 1 dA over dt, equals, pi is a constant, leave it alone. What's derivative of r squared? Well, that is just 2r, but then you got to do times the derivative of the variable, which is dr with respect to time, over dt, because we're taking the with respect to time. So I'm trying to show you guys patterns on this thing. So you can clean this guy up, make him look good. So dA dt would be 2 pi r dr dt. And you begin to catch a pattern. But remember, take derivative with whatever you're doing with respect to. Now, what's the point of all this stuff? Well, your professor is going to go into great detail about these word problems, and they can get pretty hairy because you're going to be the one having to come up with the formula for the scenario that you're talking about. If you're talking about a right cone and you got some kind of rate of change of volume coming in this thing, well, that's a volume, which means you got dV dt because it's rate, and you got volume equation of a cone is 1/3 pi r squared h. So you're going to have to start connecting all the formulas with what's given. So here's a simple example of that. Again, your professor is going to go into the great hard word problems of this. We're just trying to introduce you to the concept. Here's a classic related break problem. I'm giving you an equation. Usually they don't give you this. You're going to have to read the problem and come up with whatever scientific formula connects all the information together. But in this one, I'm giving it to you. If z squared is equal to x squared plus y squared, and dx dt is equal to 10, and dy dt equals -1, we need to find dz dt when x equals 5 and y equals 12. Now, that being said, another way I could have worded this would be some kind of, I don't know, maybe distance formula where x squared plus y squared equals z squared, so that's some kind of Pythagorean theorem type of kind of formula here. And the rate of change, so this is what I'm after. The rate of change of x with respect to time was 10 inches per second or something like that. I don't know, I could give you some units or something or other. Per is a key word that's going to be a rate. But the rate of change of x with respect to time is 10. The rate of change of y with respect to time was -1. And we need to calculate the rate of change of z with respect to time when x equals 5 and y equals 12. So you get to see that you can actually start throwing this stuff into word problem format, and these are very, very important word problems. These are the type of things that really start throwing in your science and engineering background stuff. So, but the goal is we need to find dz dt. So the first thing I got to do is come up with my equation that links it all together, which I was given in this one. Usually you're having to go find this guy yourself. But z squared equals x squared plus y squared. Since I want to find dz dt, I'm going to take derivative of my equation with respect to time. This is going to give me, well, let's see here. Derivative of z squared would be 2z, but every time I take derivative variable, I'm going to tack on that times d variable, dz in this case, dt, equals, what's derivative of x squared? Well, that would be 2x, but times derivative inside, derivative of x would be dx dt, because we're taking derivative with respect to time with all these problems. Plus, keep on going until you're through the equation, derivative of y squared would be 2y dy dt. Every time I take a derivative variable, I tack on that d variable dt. We'll plug in what we know and solve for what we don't know. See, I'm trying to find dz dt, so treat this guy as a variable. So this will be, if you look at this thing the right way, this is 2 times z, which is going to be an unknown. The dz dt is going to be the variable that I want to try to solve for. That'll be equal to 2 times x times dx dt plus 2 times y times dy dt. And I wrote them like this so you can see that I'm literally just going to plug in numbers because, hey, I'm given most of these guys. Let's see here. Let's start over here. There's 2. What's x equal to? Well, they told me we're supposed to find dz dt when x equals 5, so I'm going to replace x with 5. And dx dt, they gave me that. dx dt was given to be 10. And there's that 2 there. And y was given to be 12. We can do that. And dy dt, that was given, and that was given to be -1. So you notice you start plugging constants into your equations to be able to get these guys in. But the only thing I need to know now is what is z, and then I could actually solve this thing. But notice up here, that's the one they didn't give me. That figures. They always give you almost all the information. Well, if they didn't give it to you, that meant that you should be able to go back and find it. So I need to figure out what z is, because there's the 2. I need to figure out what the z is to plug in there so I can solve this thing. Well, if you don't know it, go back to the original equation. Z squared equals x squared plus y squared. Now that would be z squared equals, I do know what the x number is. X was 5. 5 squared plus y, that was 12 squared. So z squared equals 25 plus 144. So, solving this thing out, this tells me that z squared is equal to 169. And then take the square root of both sides, and this was supposed to be distance, so you're supposed to know you're supposed to take the positive square root. I made up these problems, so trust me. You're supposed to take the positive square root, but officially you're right, it's plus or minus, but z was supposed to be positive here, so I should have listed that somewhere. All right, well, tell you what I'll do. I'll come up here and go, hey, Ryan, z is greater than 0. Okay, let you know about it. So there's my z. And so what my point is, if they didn't give you the variable to plug into your derivative equation, you typically can go back and plug in what you do know and solve for it. So z is equal to 13. So let's clean this up a little bit. This gives me 2 times 13, which is 26. dz dt is equal to 2 times 5, which is 10, times 10 is 100, plus 2 times 12, which is 24, times -1 is minus 24. So 26 dz dt would be equal to 100 plus negative or minus 24, and that would be 76. And then I'm going to divide, so dz dt would be 76 over 26, and we could use our calculator or just reduce it if you'd like, but I'm going to try to give you all aspects of your number here. So reducing it gives me 38/13. But for you engineer types out there, you guys would be happier with this answer. 2.923076923. And of course, the reason why I'm showing you this because web work would take any of these guys. But so there's my answer. The dz/dt is 2.923, and maybe this will be feet per second or miles per hour or some kind of distance. I was leading you on to this, but the reality is that what I did here is the way you typically do most word problems. The problem you're going to have is it's word problems. So you're going to have to take the words and come up with the formula, and take the words and come with the variables and which rate is what. So y is x dt is 10, y is dy dt -1, so forth and so on. And that's what your professor is going to be really focusing on in class. So it's a big section, so study hard, but this gives you the foundation of the idea of what you're doing and why you're doing it and stuff. So I hope this has been helpful, and I'll see you on the next video.